So tonight's lecture is part of the online lecture series organized by Peking University on the occasion of the centenary of Bertrand Russell's visit to Peking University, which happened in 1920 to 1921. Now it's my great honor and great pleasure to introduce our speaker, Professor Colin McLarty. Professor McLarty is the Truman Palmley Handy Professor of Philosophy and of Mathematics of Case Western Reserve University. He is currently the chair, or chair again, of the philosophy department there. Professor McLarty is a well-known scholar in the field of logic, history, and the philosophy of mathematics. He is an editor of the Journal of Symbolic Logic, and he is the former president of the Philosophy of Mathematics Association. Professor McLarty is also a frequent visitor to China, where he taught, as far as I know, he taught category theory and philosophy of math in Beijing. Now, without further ado, let us welcome Professor McLarty to deliver his lecture, Mathematics as a Love of Wisdom. Professor McLarty.
Okay, thanks. It's nice to feel like I'm in Beijing. It's nice.
Yeah.
We can't travel. This is a picture. This is Saunders Mac Lane. He's surely best known as one of the creators of category theory, but actually what made him the president of the American Mathematical Society and the Mathematical Association of America, much less known now precisely because it was very detailed technical work, right? He's remembered now for a broad conceptual idea, but what established his career was very detailed technical work in number theory. And of course, that's just the kind of thing that gets built on and built on and built on, so that then you don't go back and look at the kind that there was 60 years ago. But there isn't time to introduce all of his career, but that's him standing outside the mathematics building at the University of Chicago. Now, what I want to talk about is, okay, there's this constantly important question that's always worth looking at. What is the relation of mathematics to philosophy? There's a lot of ways to answer this, a lot of directions to take, but the more specific question, what is the relation of philosophy of mathematics to either philosophy or mathematics? These are also, people give more varied answers than I would have guessed if it was just up to me. But for Saunders Mac Lane, there was just no question about a relation between these things. There's no, because there aren't separate things here. Philosophy is the love of wisdom. Mathematics is one part of wisdom. Not that mathematics is the ultimate of wisdom, right? This is not to say, as some philosophers have tried to do, that all of philosophy needs to be made mathematical, but mathematics is a part of wisdom. That can't be changed. That's not up to us whether we feel that way or not. And so the love of mathematics is a part of the love of wisdom. It's a part of philosophy. It just is. And the philosophy of mathematics is the part of philosophy that comes from loving mathematics. It's that part of philosophy. It's not related to philosophy. It's a part of philosophy. And he's very serious about this. And as I started looking into this, what it brought me to is a philosopher that ordinarily I don't stress that much. I really like Plato. I read Plato and I think, a lot of this could be true. But this brings me to Aristotle, who I don't normally read that much of Aristotle, but this is the resemblance. So I want to talk about that connection. Here's the basic link. This is Aristotle. Well, of course, it's not historically Aristotle. The people who made this sculpture were relying on previous paintings of previous sculptures of. But this is the famous Aristotelian first philosophy that I'm going to disagree with Penelope Maddy about some of that. Aristotle tells us what is knowledge, what is science, what is wisdom. These are science and wisdom are the same thing for him. We don't have time to build all that, but we do not think that we know a thing until we are acquainted with its primary conditions or first principles and have carried out our analysis to its simplest elements. It's actually a little more complicated than that. Aristotle actually says that in any branch of knowledge where there are first principles, we don't think we know them until we know those principles. I'm not sure whether he thought we can know other branches. Rhetoric, he tells us, for example, there are no first principles of rhetoric. I'm not sure whether he thought rhetoric could ever be a good science because it didn't have them. But anyway, when there are first principles, we don't think we know a thing until we're acquainted with its primary conditions or first principles and have carried our analysis to its simplest elements. Wisdom for Aristotle is the same as what he calls science. Okay, when I say science, this is a Greek episteme. I'm not going to worry about how to pronounce it. But it's absolutely not what we call science now. It's certainly not empirical science. It's not that. It's more like what the Germans called Wissenschaft. About 50 or 100 years ago, they've started using that the way English speakers use science. But anyway, it includes, for Aristotle, it includes ethics, mathematics, metaphysics, for example. These are not what we normally call sciences today. But they are fields in which we want to know first principles and can know, according to Aristotle. Wisdom, science for Aristotle, these are two different words. Wisdom is in Greek sophia, like in philosophy. Science is, I'm translating episteme, they're not the same word, but they mean the same thing. He uses them interchangeably, at least in a lot of what he writes. I have not read all of Aristotle. Actually, I have read all of it, but I haven't remembered all of it. First principles, here's the first place where I want to disagree with Maddy. First principles are never intended to be the first things we know. No. It is not the case that we start with philosophy and then go off and learn other things. No, Aristotle absolutely certainly doesn't think anything like that. First principles are not the first things we know. They come after we know a lot of things. The natural way to reach them, he tells us, is to start from the things which are more knowable and obvious to us and proceed towards those which are clearer and more knowable by nature. I am very impressed by this passage. It's hard for me to imagine exactly what Aristotle meant by it. I know what I mean by it, and I can say some things he might mean by it. You ask a small child, what is there in the world? What is the world made of? A small child might say, well, there's mom and dad, and there's houses, and there's dogs, and there's birds, and that's what the world is made of. There's other stuff, but it's made of things like that. But we realize that those aren't very clear to us until we analyze them further. And in Aristotle's time, it's very common around there to say, well, basically what there is, there's earth and air and fire and water. And you have similar things in China around this time. Aristotle adds that there's a fifth element, ether. And those were less obvious, but they're more knowable. But today we have a long history of further developments from there saying, no, those aren't fundamental either. What's fundamental is sulfur and mercury, and I'm talking about traditional sulfur and mercury now, not the modern elements, but this medieval ideas, and oil and fire. And then we say, no, there's chemical elements. We can look back on a long history of watching, say, physics change and change and change. And at each step, it gets simpler in principle, more knowable in principle, more arcane, less natural. But Aristotle hadn't seen that. So, but he's exactly right. The way we reach first principles is by constantly advancing. I just don't know what examples he knew of extensive advances. He could see some advances. He could say, again, ask a child, how would you describe the shapes you can draw in sand? I don't know what they'll say. You could go ask a carpenter or a stonecutter. Now they've got a lot of ideas about how to draw shapes and cut them. And then you can go ask a geometer and they'll give you a different idea of what's basic here. But the natural way we reach first principles for Aristotle is to start from the things more knowable and obvious to us and proceed towards those which are clearer and more knowable by nature. General relativity is by nature clearer and more knowable than naive ideas about space. I think he's right. I think that's a correct analysis. I know a whole lot less of general relativity than I know of Newtonian physics. And I know less of that than I know of just how to, throw a ball. But I think he's right about that these things are clearer and more knowable by nature. And this is working knowledge, not just theoretical knowledge. At first, I almost said that wisdom has to be practical as well as theoretical, but remember, practical for Aristotle has another meaning. Practical for Aristotle is about making choices in life. So I would say working knowledge, it's not just theory. Aristotle tells us it is generally assumed that what is called wisdom, which is the same as science, is concerned with the first causes and principles, so that, as has already been stated, those who have experience, people who've seen stuff or maybe handled it, are held to be wiser than those who merely have any kind of sensation. They've been around it, but they haven't handled it. The artisan is wiser than those with experience, the one who can actually make things. And the craft masters are wiser than the artisans. The people who can direct work are wiser than the people who can merely do skilled work. I mean, I've picked these because of their relevance to Saunders, to MacLean. So in short, he says that wisdom, science is better than acquaintance. It's even better than experience in three related ways. First of all, science can be taught. Oh, I lost that. Oh, yeah, I lost that slide when I was revising this. He tells us that the mark of wisdom is the ability to teach. I like that. Professors, you have to like that. Aristotle's not saying those who can do and those who can't teach. No, he's saying the mark of wisdom is that you can teach it. That's how we know that somebody can. It's not just that they can make a bridle, they can teach people to make bridles. It's experience. Science, unlike mere experience, can be taught. Science gives the why of things. It gives the first principles. It explains why they happen. And science makes one able to direct others. So I'm going to call this Aristotelian naturalism. Naturalism, of course, is a word with lots of meanings. And here I'm not disagreeing with Pen Maddy about it having lots of meanings. That's why she writes books on what she means by it, because there's lots of things you could mean by it. I'm going to take it sort of in the basic direction of it is that a naturalist philosophy thinks philosophic knowledge is not different in kind from other knowledge. You're knowing about the same stuff. And what you're knowing, you're not just knowing lots of facts, you're building scientific knowledge. The special sciences for Aristotle are parts of philosophy. It's not at all clear to me for Plato that Plato's not interested in writing about special sciences. Aristotle does all the time, a great deal. We have lots of his. And they're not things you would philosophize about. Aristotle doesn't say, okay, there's this thing called physics and here's philosophical thoughts on it. He writes physics. Of course, it's a very different thing from what we call physics now. He writes physics because that's part of philosophy. We know a thing when we found its elements and simplest parts, or at least if it has them, that's what it is to know it. And we begin what's more knowable to us, and we move to what's more knowable by nature. He tells us the same things are not knowable relatively to us and knowable without qualification. Aristotle absolutely understands what I was just saying about general relativity. Of course, he's not saying about general relativity. He absolutely wants to say the best science is knowable without qualification. It's simply knowable. It's more knowable than other things. Doesn't make it more knowable to us. General relativity is in some way harder for me to learn than Newtonian physics, and yet it's more knowable. Newtonian physics has lots of gaps when you think about it. And how do we fix those gaps? We do fix those gaps. Physicists fix them by moving to general relativity. Well, that's a simplified history. But yes, what's knowable by nature is the best knowledge, but it's not the most knowable to us. It's effort for us to reach it. For MacLean, mathematics is exactly like that. In mathematics, by the 20th century, anybody who knew any serious mathematics knows mathematics is not the accumulation of theorems. There's way too many theorems for your brain to accumulate. So you can't learn this by learning one theorem after the other. Not possible. You have to know the order of it. To know the order of it, Saunders Mac Lane believes, what not every mathematician believes, that to know the order of mathematics is to know its simplest parts. Now here, we as philosophers have maybe misled ourselves by doing something I do too. When we think about knowing the order of mathematics, we think of foundations. I think of foundations. Saunders thinks of foundations. Not everybody does. You have mathematicians. Carl Friedrich Gauss, the great Gauss. He learns vast amounts of mathematics, no interest in saying what the basics are. He wants to know what the whole structure of it is. But we tend to think when we describe mathematics, we describe it in terms of the basics, that mathematics gets its order from basics. And I tend to think that way. I do want to suggest, especially to graduate students who might be thinking of philosophy of math, you know, to take a Chinese example, Xing Chen. I'm not, you know, here's someone who knows huge amounts of mathematics, not starting from foundations, not starting that way at all, starting from fiber bundles in geometry and making it a very huge, extensive. But as in philosophy of math, the people we talk about believe we know we can organize math by finding its elements and simplest parts. And that, including myself, that's what I do. So for Saunders, to know mathematics as a whole is to know its simplest parts and the whole order. It's not enough to know the simplest parts. You look at Saunders's book, Mathematics, Form and Function, which, by the way, you should look at. If you're interested in philosophy and math, you should look at Saunders' book. It's an amazing book. There's a whole lot of math in there. I mean, you learn a little complex analysis, which you don't from most philosophy of math books. But it is still true that it starts with fundamentals. It starts with foundations for Saunders. Again, I don't mean starts historically. I don't mean that's the first thing you need to know. I don't mean that's the first thing anybody knew. But when you're organizing it, it rests on foundations for Saunders, as all knowledge does for Aristotle. And those foundations are more knowable by nature without being more knowable to us. Saunders absolutely does not believe that the foundations are the first things that make sense to you as an individual learning math. They're the way to make sense of mathematics as a whole. And I mean this very concretely. Let's look at two questions for Saunders. There's this paradigmatically philosophical question. What are mathematical objects? Hey, that's two questions. What are mathematical objects? How do we come to know them? Okay, I've labeled that as one question, but it's two questions. Okay. What are solutions to a partial differential equation and how do we come to know them? I'm afraid for most philosophers of mathematics, these questions are unrelated. The way you answer the first question is to learn Zermelo-Fraenkel set theory. That'll tell you what mathematical objects are. They're the sets in Zermelo-Frankel set theory. It's widely understood, though, that this will not help you learn the theory of partial differential equations. These are just two different things. But for Aristotle, they are not two different things. For Aristotle, the way you know any science is to know its first principles. And for Saunders, these are not two different questions. And I mean this very concretely. For Saunders, the question of solutions to a partial differential equation can only be a special case of the question of what are mathematical objects in general. You have to answer the two of them in related ways. Saunders, during World War II, Saunders was put in charge of a division of the government. It wasn't just all at his university, but of a large body of people doing mathematical research. And in that mathematical research, one of the things they're doing is solving a lot of partial differential equations. They want to know, how does a boat move through water? What's the most efficient hull shape? They want to know, how does a bomb fall through the air given wind resistance? So we're doing a partial differential equation here. They want to know, how does an airplane wing move through air? They're solving differential equations, and Saunders knows that they're solving them in many different senses. This is Aristotle's widely quoted as saying, he tells us, being is said in many ways. There are lots of different senses of being. A thing can be a certain color. A thing can be in a certain room. For Aristotle, there's a lot of senses of existence. Well, there's a lot of senses of solutions to partial differential equations, too. People don't always know this, but Saunders knew it very well, not out of intellectual interest, but because he's supervising. Remember, that's the ability, what wisdom gives you the ability to do is the ability to supervise for Aristotle. And he is supervising work solving partial differential equations. One sense of a solution to a partial differential equation is it's a function that meets that equation. It's a function whose derivatives are related to each other the way, and I think to most philosophers of math, that's the meaning of solution to a partial differential equation. It simply means a function whose derivatives are related the way the equation says. And this may be very hard to find, and it may not exist for all initial cases, but that's what solution means. But this is not the only thing it means if you're doing actual research on how boats move through water. You have to know that a solution to a differential equation can also be a symbolic solution. It can be an expression written in terms of previously known functions and previously known things that aren't necessarily functions. I don't have this on the slide, but people probably know of the Dirac delta. We say delta of x it's a function that's zero everywhere, but when you integrate along the whole line, delta of x times a function, the value is the value of that function at zero. We call it generalized function. You calculate with it like it was a function. I'm not going to try to explain it in more detail right now, but it's fun to learn. It's fun to learn. It's in the paper. It's in other stuff. We use symbols. We calculate with these symbols, even though they don't define functions. The simplest example of that is, of course, 1 over x. You know how to calculate with 1 over x. You know that 1 over x times x equals 1. But you also know that 1 over x is not defined when x equals 0. And yet its product with x is equal to 1 all the time, we commonly say. Of course, there are precise technicalities you can get into here. But if you're actually doing work in partial differential equations, you're using things, to say the least, like 1 over x, not caring where they're defined or not, because you know the rules for calculating with them. So symbolic equations could be very familiar functions, like the sine, the cosine, polynomials, but they don't have to be functions. They can be expressions that are not, to say the least, not defined everywhere. There are weak generalized function solutions, which are not all symbolically expressible. The way these are invented was by coming up with theories of symbolic solutions that didn't have to be real functions, but generalized functions are not all expressible, whereas symbolic solutions are. and more, including notably numerical solutions. Numerical solutions are another kind of solution. The relations between these have not been explored by philosophers as far as I kind of wish they would be. I got a paper on that. We had a whole meeting on about a paper that Lydia Patton wrote about the Navier-Stokes equation, and Susan Sterrett and Eric Curiel. We gave talks about this. This is something I would encourage philosophers of math to look at partial differential equations, because it's really exciting stuff. And in the theory of partial differential equations today, mathematicians are still coming up with new senses of solution. I don't mean they're finding new solutions. They are doing that too. But they're finding whole new things you could mean by a solution. And this for very important and comprehensible reasons, which currently are being beautifully described by Terence Tao. I mean, he's putting it online. If you want to watch mathematics being done live before it's very clearly understood, I mean, there's vast understanding in there, but it hasn't reached its end. You can read Terence Tao on partial differential equations. But this is something that Saunders already knows, Saunders Mac Lane already knew in World War II as he's supervising research on these things. We're still finding out what we mean by solutions to a differential equation. And for Saunders, the standards for answering these questions are like the standards for answering what is a number, with the difference that asking what is numbers is not really very important right now. They've got really good answers to what do we mean by a number. Philosophers still want to debate what is a number. Mathematicians, the reason they don't debate it isn't that they don't care, it's that they know in current terms. Understanding changes with time, but they've got a perfectly stable structural understanding of what are numbers right now. They do not have a stable final understanding of what are solutions to differential equations. But what I want to urge is Saunders' perspective, which I claim agrees with Aristotle's perspective, that the question, what are mathematical objects, what are numbers, has to be seen as related to what are solutions to a partial differential equation. You know, in both cases, the first standard for the answer, which Dedekind already told us about numbers, is it's got to work, it's got to advance knowledge. And this is a complicated issue, advancing knowledge. For Mac Lane, as for Aristotle, questions of the special sciences, notably including mathematics, are questions about wisdom. They're questions about, they are part of the love of wisdom, the pursuit of wisdom. They can't not be. Now, let's be very clear. What philosophers are constantly saying, and it's not wrong, a mathematician can learn a technical answer to what are solutions to a partial differential equation without ever asking the philosophic questions. And believe me, I've seen this happen live. Philosophy and mathematics professors at very prominent schools will sometimes encourage their students not to ask the philosophical question. Because you're a student, you should be moving ahead. You're trying to win a Fields Medal. Don't worry about basic questions. Go win a Fields Medal. You got to. So you can learn a technical answer to what are solutions to a PDE without ever asking what are mathematical objects. But in exactly the same way, you can learn an answer to what are mathematical objects from convention debate. Go to philosophy convention. That used to happen. People used to all get together in the, now you know what I'm saying. I mean, you can learn an answer to the philosophical question by reading journal articles without ever asking about actual mathematics. You can approach either of these questions without the other. And lots of people do, and probably lots of people should for different purposes. I will say the answers to the mathematical questions are more stable, in fact, than the answers to the philosophical ones. They change less over time, but you can answer the two. But for Mac Lane, separating these questions, these are both failures of understanding. You are not understanding if you ask one of these questions without the other. Of course, you should focus on one or the other. When he was talking to people about their work during World War II on ballistic motion through water, he didn't want them asking what are numbers, but he did want them actually asking What kind of solution to the equation do I need here? Do I need a numerical solution? Do I need an exact solution? Should I just use a symbolic solution? You have to, and how do you decide what kind of solution to know? You have to know the good of each one. You have to know what each one is for. You have to know all the kinds to choose the kind you need, and you have to know what each kind is good for to choose the kind that you need. When you're actually solving a problem, you would like to work with exact solutions. You'd like to work with exact symbolic solutions. You'd like to know a simple expression in familiar terms that gives a function that solves this. But even if you can know that, which you can for some problems, but even if you can know it, in the end, you're going to need to switch over to numerical solutions to get specific answers in a concrete situation. And you need to know when. When do I leave the theoretical, when do I leave the function realm and go into numerical solutions? When do I leave the symbolic realm and insist on actual functions? You need to know the good of them. At least you need to if you're going to supervise work. That's the connection with Aristotle. Remember, wisdom's what makes you a craft master, makes you able to supervise. I will mention an issue, and I don't know whether to leave this issue aside or mention it. When you read Aristotle in translation into English, a lot of passages he talks about what men do when they understand. The word man is not in the Greek. It is not gendered in the Greek. So that's why I went to craft master. The word there isn't gendered. For MacLean, separating these questions is a failure of philosophy, no matter which side you go on. Not that you should never question them, because you shouldn't always be pursuing philosophy as a whole. But you should know how to put them together. If you don't, that's a failure of philosophy. So compare Penelope Maddy's Second Philosopher. Penn has written a lot to define what she means by this. I will tell you my experience, and I think it's the same as hers. It's a lot easier to think, I want to be a naturalist. I want my philosophy to be of one piece with my scientific knowledge. It's a lot easier to want that than to say what it means. So she's trying to articulate this. Her Second Philosopher, as some of you will know this and some of you won't, this is her idea of what kind of philosopher she wants to be. She wants to avoid first philosophy. First philosophy means beginning from first principles. We're going to establish the philosophical, Descartes' project. Descartes really does say we should find the first principles before we believe anything and then build up from them. Now, why he says that is a more complicated question, but he says it. And she's against that. And she feels that Aristotle is this way. Aristotle says we need to start from first principles, philosophical first principles, and build up. This is not what Aristotle says, but certainly not what her Second Philosopher says. The Second Philosopher doesn't start from philosophical principles. They arrive at philosophical principles by starting with the great sea of all there is of science. In particular, the Second Philosopher sees fit to adjudicate the methodological questions of mathematics, the basic philosophical questions of mathematics. What makes for a good definition, an acceptable axiom, a dependable proof technique? How do we answer these? Well, by assessing the effectiveness of the method at issue. If you want to evaluate what are the good methods, see how effective they are as means towards the goals of that branch of mathematics. Don't see how effective they are at winning debates at a philosophy convention. Don't see how well you can write an essay about them. See how well they help to advance the goals of the stretch of mathematics involved. That's going to be Second Philosophy. We don't judge new methods by thinking about them. We see how they work for the special science involved. Well, all active mathematicians do some of this. Again, if you're a doctoral candidate in mathematics, you may very well have your advisor sometimes tell you to do a little less of that and write the dissertation. Stop evaluating and start writing. They may tell you to do that at some moment. But everybody evaluates the effectiveness of methods as ways of reaching the goals in their field. And just because your advisor sometimes tells you not to do that doesn't mean even your advisor doesn't want people doing that, just wants you to finish your dissertation. All active mathematicians do that, and some of them do it a lot, and Saunders did it a lot. One of the differences with Saunders is he was actually hired by the federal government to supervise writing reports. I'm not talking about him supervising the math work now. He was supervised to write studies over what kind of math should people be learning, what kinds of mathematics should the government be encouraging in universities, what kinds of mathematics should a given mathematics department, like his department in Chicago, what kind should they be studying? He does a great, and he writes about this in reports. Some of them were classified during the war, but you can read them now. But here's the difference of Saunders from Maddy's. Maddy, I think Saunders' work is a natural. If you're interested in Penn Maddy's naturalism, you really should be reading Saunders, because he's doing something very much like that with vast information and with vast actual effect on the practice of mathematics. But there's differences. Saunders was much more attuned than Maddy to the practical unity of mathematics. Maddy likes to talk about each branch pursuing its own goals. This is not crazy. There's good purpose for that. And there's an especially good purpose in the context of her project, which is to understand research on the continuum hypothesis in Zermelo-Fraenkel set theory. That's quite a specialized branch of mathematics, and it really doesn't take a lot of values from other parts of math. She writes about how in the development of set theory 100 years ago and more, and that's really a good way to put it right now, because I'm talking before 1920, the same 1920 when Russell arrived in Beijing. Do you picture Russell arriving in Beijing? I think he was mostly inside the Second Ring Road. I'm not sure about that, but I think he was. And Maddy writes about how mathematicians at that time, how set theorists at that time were taking their ideas from analysis and relating them to analysis. But she also feels that time is over now. It's time in the current research on the continuum hypothesis. You don't worry about what the analysts are saying. You worry about what's been developed in Zermelo-Fraenkel set theory. Again, that's not crazy, but Saunders is much more on the other side, that all of mathematics needs to relate to all of mathematics all of the time, at least at the top level. The craft masters, the people who have business supervising, need to be looking at the practical unity much more than Maddy talks about. And Saunders was explicitly called on by the US government to report on these things. You can read these reports. There's, well, I won't go into that part of his career, but, and most importantly, here's the big difference. Saunders knows that you cannot have a science simply by trying to reach the goals of that science. Maddy is very interested in, we've got the goals of the science, we're going to try to assess methods in terms of how they reach those goals. But Saunders knows what Maddy also kind of knows, but she doesn't emphasize it, and what Aristotle certainly knows, you have to assess the goals too. You can't have a science by just having goals. You have to evaluate the goals. Forming the goals is part of the science. And Saunders was very keenly aware of that, and he writes about how to do that in, say, his book, Mathematics, Form and Function. Mathematics for Mac Lane was not a branch of engineering. It was not. Okay, I take engineering here as a figure where often the engineer is told, here's your goal. We need to increase fuel efficiency in this line of cars by 10%. Here's the basic design. We need to change it. We need 10% higher fuel efficiency. And we need a lot of other things too. So now, how can you meet this goal for us? The engineer doesn't choose the project of increasing the fuel efficiency. But mathematics does choose its own projects. Engineering by itself reaches goals that are given. But the sciences, each one as a whole, also chooses its goals. And this is missing, and I think too much in Penn Maddy's work. It's not missing for Saunders at all. Of course, mathematicians choose their goals. Besides seeing what will reach them, they also choose them. in research and in education. Saunders was very interested in education. He mixed exposition with research throughout his career. Okay, yeah, here's that quote from Aristotle. In general, the sign of knowledge or ignorance is the ability to teach. So we hold that art rather than experience is knowledge. Some can teach, some cannot. If you're a little puzzled what he means by art there and how he knows that art is the same as teaching, so am I. And I think in general, it's good to be puzzled by that because it's not obvious. It's something, you know, specialists have studied it. It's not that nobody's thought about this before. But it's not a settled question. This is something to puzzle over. But I think Saunders would have agreed with this entirely. He does. One of the reasons he becomes a founder of the Mathematical Association of America around 1950, after the American Mathematical Society already exists, is that the MAA is going to talk about teaching much more than the AMS does. For Saunders, absolutely, the sign of knowledge is the ability to teach it. That's what it's. Again, Aristotle, I come back to this quote, Aristotle makes this as a theoretical demand on philosophy, but for Saunders, it's also a practical. You do this every day. We do not think that we know a thing until we are acquainted with its primary conditions or first principles and have carried our analysis to its simplest parts. And he wants to do this. And you see him doing this over and over and again in his career. He goes to Gottingen, he sits in classes with Emmy Noether. This is wonderful. Emmy Noether, her actual mathematics deserves to be known much better than it is. The reason mathematicians don't know her mathematics today is that they were taught it as undergraduates where they weren't being given the name of who did this. They learn it without knowing that it's her. But people who study Emmy Noether, we look too much at her algebra and not at her whole view of mathematics. Saunders goes and takes these classes and he's amazed and he keeps thinking, ooh, there's something more fundamental. He even decides he can be more fundamental than that. Throughout his career, he's constantly taking deeper cuts into a subject, deeper senses of understanding. The extreme of this, of course, is the general idea of a category. And philosophers of mathematics will sometimes say, well, that's too abstract. That's not real understanding math. Saunders would absolutely agree that if all you know is category theory, you don't know math. But he'll also tell you if you want to learn math, you really want to structure it by category theory, right? That's the latest in going deeper on finding first principles. Knowledge is understanding. Knowledge isn't accumulating facts. A lot of people say this, notably Aristotle and Saunders Mac Lane. I think they put it together. Saunders eventually, not when he went, when Saunders went to Göttingen as a doctoral student, he really did think, we're going to get the foundations of math right and it'll all build up from there. He looks at philosophy of mathematics, Principia Mathematica, Russell and Whitehead, Principia Mathematica, and he says, this is terrific. This is how math needs to be done. And I'm going to do it this way. And it utterly fails. It utterly fails. He realizes you can't build it up from there. In Göttingen, he learns you're not going to build it from foundations. He runs into Hilbert's Epistemology of Mathematics. And here's some German. Wir müssen wissen, wir werden wissen. Hilbert loved this phrase. It's on his grave. We must know, we will know. This is where mathematics begins with Hilbert. It doesn't begin with logical foundations. It begins with saying, in mathematics, there's nothing we won't know. Gibt es keine Ignorabimus. I keep going to the German. In mathematics, there's nothing we won't know. In mathematics, we have to know, we will know, it will all be known. And Saunders absorbs that and says, no, we don't start from foundations. We start from all there is and the fact that we can know all there could be. He studies he studies philosophy with Weyl and Geiger. Again, if you're interested in naturalistic philosophy of math, how would somebody approach mathematical questions if their goal was to do mathematics? Good question. Penn likes to press this question, but understand it's been done. You should go read these people. They might have been not done it right. They might be wrong, but it's been done. You should read the people who are doing it. Hermann Weyl, for example, David Hilbert. Moritz Geiger, he's a philosophy professor. He learns some math. He doesn't do mathematics. In Gottingen, they taught him that mathematics is a science of forms. They taught him this sort of proto-image of math that you can see again in category theory. I won't go into all of that. Phenomenology. They taught phenomenology. In Gottingen at that time, philosophy meant phenomenology. From Emmy Noether, algebra as the future of all mathematics. All mathematics would be made algebraic. Well, you read complaints about this today. All of math has become so algebraic. Yeah, well, to Noether, that was a good thing. She wanted that, and she got it. A lot of it does happen. He's bitterly disappointed with his foundations, with his dissertation. Saunders Mac Lane, very disappointed with the work he did. He thought that all you had to do was improve Principia Mathematica, and now you'll have a whole new approach to math. No, you don't do it from the first principles. You do it arriving at first principles. You arrive at first principles, and for Saunders, there's no absolute first principles. I'm not sure about this for Aristotle. Were there absolute first principles? Once you arrive at them, you've got them, that's it. I'm not sure about that for Aristotle, but I'm absolutely sure for Saunders, no. No, in mathematics, there's no ultimate first principles. The current best organization is category theory, but there's no ultimate first principles for Saunders. There will be no purely philosophical philosophy of mathematics. There'll be no purely mathematical philosophy of mathematics. That would make math into engineering. All you'll be able to do is solve problems that came from who knows where. There's no purely philosophical philosophy of mathematics. You don't build it up from first principles. You do all of that. You do all of it together. And he gets this partly from what he learned. There's a historian of ideas now, Alma Steingart. She was lately a member of the Society of Fellows at Harvard. Okay, that was 5 years, it's over. But she's been especially stressing what applied mathematicians did in World War II in relation to pure math. And Saunders is an important figure for her in that. For Saunders, that's where it all comes from. It's all together. It's all together. You could understand math by just starting with set theory, but it won't be a very good understanding. You could understand math by just starting with design of airplane wings using partial differential equations. Also won't be a very good understanding. You need it all. So all the way down to foundations with Eilenberg. That gets to what he meant by foundations. After his dissertation, he felt very strongly there will be no ultimate simplest elements. Because he really felt, and you can compare what Steve Audi has written about this. Steve takes up that very same thing. For Saunders' book, Mathematics, Form, and Function, ends with questions of truth and beauty in mathematics. He calls them the philosophical questions. He knows that philosophers don't ask them much. But you need to ask questions of truth and beauty, he tells us, both to make your mathematics more concise, to learn what to focus on, so you get into manageable, small, key insights, but also for vision to know where to go in the future. You need philosophical insight for that. Understand that for some, can philosophers do this? This is the thing. There's a very strong feeling in philosophy of math. We don't change mathematics. We want to understand math. We don't change it. Okay, you understand that that's completely inconceivable to Saunders Mac Lane. Of course you change mathematics. That's what you're here to do, is change mathematics. But do it right, not wrong. Right? You could get it wrong. A lot of people have got it wrong. But changing math can philosophers do this? Is he kidding? I mean, for Saunders, this is obvious. Only philosophers can do this. Understanding that philosopher does not necessarily mean people in philosophy departments. Saunders does not believe that philosophy departments should tell math departments what to do. He does believe that mathematicians are philosophers, and that you need that perspective to talk about the direction of the subject, to talk about the future of the subject, to find the best methods in the subject. Okay, well, that's what I've got. I will mention
So,
that in all the times I was talking with Saunders Mac Lane, he could be very critical. He told me I had a lot wrong, but he never, ever said that what I was doing wrong was that I was a philosopher and shouldn't be talking about what mathematicians should do. He did often say I was wrong about it. But it's not about where your degree is, it's about what you know.
so Colin, that's the end, or?
Yeah.
Okay, so first let's thank Professor McLarty for the excellent lecture. And are there any questions? Oh, there are some questions. Yanjing, you want me to repeat to the speaker, or?
Yeah. You mean in the chat, right?
Yeah, there are some questions.
There is one in the chat, so you can read that.
Okay, so let me see. So there's one question by the. So may I ask you to elaborate further on how the questions of truth and beauty could facilitate a concise breadth of vision in mathematics?
Yeah, I think on the question of truth, this is something that philosophers of mathematics have systematically underemphasized. And I'll go back to the question of what is a solution to a partial differential equation? What are the true things to know about an equation? It's not obvious what you want to know about an equation. We think, oh, it is obvious. You want to know what functions solve it. But suppose I take the Einstein field equation. I take this partial differential equation for space-time. And I say, I've proved that there's this solution that has such and so properties. And somebody says, okay, but what is the solution? I say, oh, well, you can't express it by named functions. I can prove the solution exists, but there's no formula for this solution. I can't express it that way. And you say, well, okay, but then what is the solution? Can you calculate numerical approximations to it? And so I have to say, well, approximation in which sense? I can calculate approximations in this sense or that sense. What is there even to know about a partial differential equation is a much more complicated question in actual fact, in actual practice, than philosophers tend to think it is. What is there even to know? What is the truth? Truth is what there is to know. I'll take that for granted. But what is there to know about a partial differential equation? People are constantly coming up with new ideas. Terry Tao writes beautifully about new concepts of what it even means to solve a partial differential equation. These are not concepts that meant to replace the old ones. No, of course not. The old notion of an exact solution, a symbolic solution, these are not going to go away. But to answer them, we're going to have to come up with new senses of solution, new whole concepts of truths about this. We need to be asking these things. The question of what is two, does two exist? That's kind of not on the agenda right now for most mathematicians. How can numbers be structures? This has been known for 60 years in mathematics. Philosophers might not like the answer, but it's well known. There are perfectly good structural ways of doing arithmetic, and everybody in number theory uses them, and they don't want to talk about them. What is a solution to a partial differential equation? Not perfectly known. Current research question, extremely important research question by Terence Tao, Charles Pfefferman, Fields medalist pursuing these. What do we even mean by the truth about a partial differential equation? Saunders wants people asking these questions and saying they do relate to fundamentals. Don't think of this as a purely technical question. You better relate it to what is a number. You better relate it to the most fundamental if you want deep answers. And it's very easy to see how to take Tao's answers to these and relate them to more fundamental questions. And beauty, oh boy, nobody much talks about beauty in mathematics now. They really don't. And Saunders doesn't have a lot to say about it either. But what Saunders does have a lot to say about is that a philosophical understanding or a useful mathematical understanding. This is not just for the philosophy department. Students finishing PhDs in mathematics right now need to pick which are the beautiful parts. They don't have to call it beauty. They don't have to call it, they could say, this is the most fruitful approach. This is currently the most productive, you know, but for Saunders, finally, that is the question of beauty. Just knowing whether some formula of set theory follows from the Zermelo-Fraenkel axioms is pretty useless if you don't know more deeply why that formula matters, right? What matters about the continuum hypothesis is that it's beautiful, right? We know, surprisingly, the continuum hypothesis is very rarely used in analysis. It isn't an important technical point for most purposes, but it's an irresistible, conceptual, beautiful question. You can't not care what is the cardinality of the continuum. And for Saunders, that's because of beauty. Saunders was specifically skeptical of a lot of how that's done. He thought it was ugly. But for Saunders, basic questions of truth. What is there to know about a PDE? This needs to be answered as a basic question. What should research be doing? Sometimes the Air Force is going to come to you and say, we need a better wing for this airplane. But a lot of the time, you're going to be saying, where should math be going? You're going to be picking questions, goals, as well as solutions to goals. And for Saunders, that's beauty. That's something you should know about. These are philosophical questions, which very important to grasp, but for Saunders, that does not mean the philosophy department has the best answer to them. But they are philosophical questions, and it's certainly the philosophy department's business to be worried about them. Just don't think that as a philosopher, you can go tell the mathematicians what they should do.
Okay, I guess there are further questions maybe related to the one you just answered. So I'm reading the question now. By mentioning choosing goals in mathematics, do you / Mac Lane think that there are indeed some topics in math which we should not look into too much?
Oh, well, here we have to distinguish me from Saunders, which is easy to do. I'm not that much like Saunders, but Saunders was very outspoken about some topics that don't need to be pursued very much right now, the way they're being pursued. And he caused some anger among set theorists by criticizing some work on large cardinals. Now, I think there are two things to say. One is what the set theorist did. You don't know the work, so don't criticize it. And there was some truth to that. The other is what Saunders said. It's not related to the rest of math. Admitting increasingly people do make connections. I do think that sometimes camps get set up, and they shouldn't be set up. I think there are more perceived rivalries than real rivalries. But of course, decisions have to be made. You go to the NSF, you sit on a panel at the NSF, they get a bunch of grant applications. That panel is going to decide this subject should get the money and this subject should not, right? And they have to do that. They have to do that. Choices have to be made. Here's a place where philosophers would be well advised, professional philosophers, to have a certain modesty. Do not try to figure out what math should be done and what shouldn't be done. I'm not going to try to do that. I don't think most of the philosophers of math I know have no real business doing that. But the choice does have to get made. Yeah. Classical invariant theory, the kind of invariant theory that Paul Gordon was doing, and that Hilbert largely wiped off the map by his abstract algebraic approach. People decided, yeah, there's open questions here. They get developed, but most people probably shouldn't be working on them. There are decisions made every day, and there should be, that certain, some subjects are just more productive than others, at least right now. There are perceived sharp conflicts over foundations between, say, categorical foundations and Zermelo-Fraenkel foundations. I certainly think people should be pursuing Zermelo-Fraenkel approaches to the continuum hypothesis. Zermelo-Fraenkel has been developed largely to work on the continuum hypothesis since the days of Georg Cantor. So I'm not, there's too much conflict here. But Saunders is right that choices get made and should be made. And it would be good if they were made on principles. We do need principles for deciding what's more and less important, because decisions will get made, and it would be nice if they were being made on principles.
Okay, next question is law of non-contradiction the first principle? Can you read the? Okay.
Oh,
sorry.
I mean, I can get the chat up. I don't have it up right
now.
It's in the Q&A, in the answer list.
Oh, I'm not right now. I'm not seeing the thing about the law of non-contradiction.
Did you click the Q&A and then you click the answered list, the second tab?
Oh.
Yeah. And you will see the second one is about the law of non-contradiction, whether it is one of the first principles.
Well, okay, I'm not good at this. I'm not getting that. Personally, I mean, I kind of worry about going to something as fundamental as the law of non-contradiction, but what I've come to over thinking about it a lot is yes. And here I can cite Aristotle. You cannot argue with people who will make contradictions. If somebody is unafraid to contradict themselves, you can't discuss anything with them. And in that sense, yes, the law of, I'm going to say classical logic really is fundamental to mathematics. It's not the only relevant logic. We see non-classical logics arise in contexts, but I'm going to say the foundations of all those contexts is in standard classical first-order predicate logic. And if you want to say the law of non-contradiction is the first step of that, I would say yes. I think Saunders would say yes. And we know that Aristotle would, because both in questions of metaphysics and of ethics, he tells us the first condition of any serious discussion is that you will reject contradictions.
Okay, any more questions from the audience?
Well, there's one more in the list.
There's one, I couldn't see it.
In the answer list. I put it there.
Well, there's this question about the Navier-Stokes equation. Yes, that is the Navier-Stokes equation of fluid dynamics.
Okay.
Lydia Patton wrote a very nice paper pointing out that in philosophy of science, we tend to say that what a scientific theory does is it limits the models that we can use in understanding the world. You take an equation, the Einstein field equation, you look at its solutions, you say the universe has to be one of these solutions, and now you know how to study the universe. In hydrodynamics, you take the Navier-Stokes equation, which incidentally 50 or 60 years ago, a lot of people had said, well, it doesn't have to be Navier-Stokes. Today, people tend to say, it should start with Navier-Stokes. You will go to other equations for special purposes, but you really should start with Navier-Stokes. And she says, why do they believe the Navier-Stokes equation? Do they believe it because its solutions resemble actual experimental situations? No, because we don't know solutions of it. We know almost no solutions of it. Navier-Stokes, like the Einstein field equation, is fundamental to a whole branch of science, even though we can hardly solve it at all. And that's why we're constantly inventing new notions of solution. not to replace the old ones, but to go along with the old ones, finding new notions of solution, because maybe we can find some solutions in that new sense, which will relate to the old sense. That the Navier-Stokes equation is concretely an important topic in theoretical mathematics as applied to the sciences. And yeah, I think it's a stunning paper that she's written. And yes, philosophy of math needs to address the Navier-Stokes equation in fluid dynamics. Not just that, obviously not just that. But yeah, we really need that. But was there another one that you were looking at?
Yeah, there's a follow-up question by the person who asked whether we should how to say, forget of some questions. Okay, anyway, so the question is, furthermore, is the problem bracket choosing among goals ethical or just sociological? That's the question.
That's a huge question. That's a huge question. And I will take a position on it that I have learned from thinking about Saunders and about Aristotle. And I'm going to say, yes, there are principles. There are principles. Mm-hmm. Some questions are more fruitful in themselves because some theories are more knowable in themselves. It will not always be obvious. What's more knowable is not the same as what's knowable to us. What's more important to answer is not the same as what we have yet understood is more important to answer. But I'm going to be very optimistic about this. This is a way of believing in philosophy, is to say, yes, there are principles that make some understandings more valuable than others, and thus some questions more valuable than others because they point more towards the valuable understandings. And this may not be at all obvious going in. It may take huge development to learn that this perspective is more fruitful than that. But I hope and believe that, and Hilbert also believes this, that there are actual principled ways that some questions are more valuable than others. And we can try to know them. We can try to. Now, if somebody wants to write a dissertation on how that's not true, yay, go for it. I don't know, it may be, but.
Okay, Yanjing, I didn't see any more questions in the list. So, but maybe Feng Kui has a question. I can't hear you, Feng Kui.
So how about now? Still cannot hear me?
Now I can hear.
Okay. Hello, Colin. Nice to see you here. Yes, we can chat more later, but yeah, I have a few naive questions. Maybe I just ask this first one. So at some point you mentioned that Aristotle think that something like we cannot know a thing unless we know its so-called simplest elements. Then at the ending of your presentation, you said something like Mac Lane left the field of foundations for mathematics. Maybe the one reason is that he never believed that we really knew the simplest elements of mathematics. So I mean, well, yeah, is that correct understanding?
Well, there's two things. What he learned through very bitter experience in Göttingen is you can go wrong by trying to start from the simplest. Starting from the simplest, it doesn't work because you don't know yet what is the simplest. You have to start with the whole subject and try to find what is the simplest. Your foundations of mathematics cannot be the starting point for work in math. They're closer. They're more like being the culmination, the end of your work in mathematics. So there's that level. You can't start from the first elements. You have to get to the first elements by starting all over the place. But the other thing is, I do not believe that for Saunders there were absolute first elements. This is always going to be relative for Saunders. I'm not sure if it was for Aristotle. Aristotle often writes as if there are absolute first principles, absolute elements. Once you know those, you've got it. I'm not sure that's the right way to understand Aristotle. I know it's not Saunders' belief. For Saunders, there's no absolute foundation. And foundations But that's different from the point that foundations are not your starting point. Foundations are something you achieve by progress.
I see. I see. Maybe just a follow-up, which might not be very relevant. So, so now we have many research which are following the approach is so-called black box approach. That means that we don't know anything inside, but still maybe we can mimic the behavior of the thing. So, so if we take literally the ideas of Aristotle, then we can never know. Yeah. So what yeah.
I mean, people who black box things commonly, again, they're not saying this is the ultimate. They're not saying this has to be treated as a black box. They're saying for right now, I can answer questions by black boxing this that you can't answer if you don't do that. They're saying right now, this is the way we get answers. But often the people who say that don't mean that this is the end of the inquiry. It's just absolutely the way to do the inquiry right now. But another thing that happens is sometimes what starts as black boxing isn't black boxing, it's just abstraction. You say, you know what? This thing where we thought we had this complex apparatus and we're going to black box it. We're going to just take it. We're just going to do the input output. We're not going to worry about what's in there. Somebody eventually says, you know what? You could just take that as axioms. You don't have to suppose there's anything in that box at all. Sometimes the result of black boxing is to just simplify the subject so that there is nothing in the box. Other times, well, yeah, you'll get into the box later, but for right now, no. When I went to Harvard, I'm going to as you know on a sabbatical. I want to study Grothendieck, and I'm talking to Barry Mazur, and I say, I want to read his seminar in algebraic geometry. And Mazur said something that he later told me to be very careful about. He said, when you're reading Grothendieck's SGA, that's this huge, it's multi-volume work. When you're reading Grothendieck's SGA, at first, do not read the proofs of the longer theorems. Don't read them, because if you start reading them, you will never get done. Don't read them at first. Now, he said, if you work in this subject, you'll want to use almost this theorem, but you'll have to change it a little bit. When you need to change the theorem, then you need to read the proof and see if that change works. And he says, if you work in this field, as he does, I mean, he's too modest to say like me, but it was like him. If you work in this field, you will eventually change all the theorems and you will eventually have to learn all the proofs, but don't learn them first because you will never get done. So sometimes black boxing is like that. Don't worry about this now because you'll never get done. But sometimes it's even better than that. And this is part of what happened with category theory. People said, we've got this algebraic topology. We're studying topological spaces by their algebra. And it's all very complicated apparatus. And Eilenberg and McLean and Steenrod come along together and say, okay, that apparatus is great. And you need it for some particular problems. But actually, it doesn't occur in your basic questions. You're not black boxing in your basic questions when you ignore it. The basic questions should have been posed and answered by axioms that don't even have to do with those details. Those are actually superfluous details for many purposes, even though they remain things you need for other purposes. So I like that. Good question. Yeah. Yeah, but when I asked Barry once, can I quote you on that, saying don't read the proofs at first? He said, no. I said, I do want to quote you on it. And he said, well, okay. But make sure not to give the impression that I said don't read stuff. Too much non-reading goes on already. Yeah. No, but what he said, don't read the proofs at first, not the first time.